DC is such a new thing. Like it's a recent thing. Yeah, the Swanee shirt kind of. Yeah, like I don't like Swanee shirt or black Swanee shirt. So I wish I had broke that. And where is the brushes wear out? But it's not against it.
So anyway, let's start then.
Yeah.
So by the way, tomorrow we went to that, so do come with any group person, finish the second lab, right? We also introduce to you another lab for the induction. So because none of the control form we have to working here, right? So we do have another lab for the induction measurement for tomorrow. So tomorrow when you come to the lab, then you have either transformer 1, transformer 2, or transformer 3, you can see that. So do come compare that. Anyway, let's focus on here. So, and on Monday, we started to discuss about the basic principle of DC motor, which you can see that from this diagram, how we can able to create the force for rotation of the conductor. So which you can see that by using this commutator, we're able to change the polarity of the current. So that in here, the force go up. Once it rotate down to here, the polarity has been already changed. So that's why the force will go down. So that's the basic principle. We're able to manipulate with the rotation, continuously rotation. So this concept is quite well-known concept. If you go through any internet or book or literature, maybe even the high school, I think somebody already taught me. Have you learned that?
No, nice.
But this diagram is very famous. We see it everywhere. Yeah.
I was gonna say, I think tonight we covered how like you can define a current loop as like an area with a normal vector or like magnetic moments.
Yeah.
Something like that, and then how like the vector of the magnetic moment has to try to align itself with the magnetic field.
Yeah. Basically, the force that come out would be we are conducting wires in here. This wire automatically generate the magnetic field. So two magnetic fields are interact with other, become the repulsion, or the other side the attraction will cause the force movement. Basically, but of course, as an electrical engineer for motor, we don't really need to understand the basic principle behind. We only need to know how to operate. So as an engineer, unless you go for motor design, the schematic design, you may need to understand how all this is. But when engineer, they only focus on control and drive, then you don't need to worry that much. But in here, this principle is like that. So we're able to use this principle to develop many different type of motor. When you open up a motor page, you can see that the motor windings could have quite many. Because each wire, one Lorentz force, two will have two Lorentz force and so on. So that's why we are able to develop a higher power motor. So that's the concept. After we've done the concept, we need to convert this into some equation for calculation and also for design. So you can see that here we got a vehicle voltage and then pass through a copper wire. Once we have any copper wire, there must be some copper resistance due to the normal resistive opposition. That's called resistor. So that's and then from the Faraday's law, we know that any magnetic induction may create a induced voltage. So that induced voltage will be actually trying to opposite the incoming voltage. Otherwise, the current will be too large. So that induced voltage, we call it E. So which in the next page, you can see that we therefore can develop an equivalent circuitry like this. Incoming voltage here, we do have voltage resistance in here, that's called resistor due to copper. Any conductor, we have resistance. And then we also have back EMF for EA. A represents for armature or winding, we call it armature. So that will come up with the back EMF created by any coil inside. The concept will be the same as when you apply any voltage for a coil, there will be some voltage developed on the coil. Yeah. And also when you changing the magnetic flux, you also have back EMF produced just like the conventional equation for the Faraday law. I think you learned them some time ago. Induced voltage equal to N d∅ dt, right? That's basically how the induced EMF created from this armature coil. So armature coil is basically a number of the coil put together, and then that will therefore create the back EMF. When we have the magnetic flux coming through like the PN, go through the coil, when it rotates, then there's a change of magnetic flux that will create this voltage. So this voltage will appear as the EA voltage here. So that's how it comes from. So happen to be this voltage will be in opposite direction to the incoming voltage that will use this method to control the current or reduce the current. Yes?
Then is EA a constant or is it a variable based on?
It must be variable. And in the next few pages, you can see how the EA being controlled by a number of parameters. I'm going to show you in a moment. That's quite interesting. So we can use EA to control a number of items, including the current and the torque, the power, many things. That's useful. So basically, a really simple model for DC motor will be like that. So you can see from the configuration, the diagram in the previous page, now we come up into a circuit. So this more look like a DC circuitry because input DC. I call DC motor because everything is DC at the moment. But in next few weeks, we're going to go a few steps further. So now the input voltage VE, back EMF EA from the divided dt Faraday's law, and the internal resistance due to wire we call it armature resistance. So the circuit are just this simple enough. Of course, I do mention to you, we do have a number of equations here. You start to remember that. So the back EMF, as John mentioned to us, is that constant? Yes or no? Because it do depend on a number of things. EA, the back EMF depends on proportional constant, KE, plus the flux. Yeah. The flux, the value amount of the flux actually control amount of the back EMF. And also the rotational speed. You see, when the motor is rotating, that will create you variation of the angle. So that will become an angular speed. So that you can see that if you plot the graph for EA against the speed, the motor speed won't look like a constant slope, right? When we increase the speed, you got higher voltage. So that's something quite important as well. Firstly, when the motor is stand still, start from zero, or the motor must start from zero, right? So the EA will be really, really small. So that's to say, if you come back to this equation, find that initially this voltage really, really small. So that means initial current could be really large, just like short circuit, right? But we do have some resistance here. So that one of the issues for most of the motor startup, because starting current will be huge. So that will affect some of the issue like the huge current, wiring problem, aging problem, initial current so large, maybe your power source or your battery or your input power from anywhere may not be sufficient. So we do need to be careful about it. That's why some people use something motor driver to control the starting current, like VSD we mentioned last year. Right? So that is to say, now the voltage will be in such a way. So the slope here, the gradient here are related to the K constant plus the phi. K is a constant related to the machine design. So when you make a machine, then you can measure the K constant, and then that will come out from the manufacturer. And the magnetic flux is the one we excite the winding using that kind of magnetic flux. It can become from the PN permanent magnet or come from external coil to create you the magnetic flux. So magnetic flux will be in the unit of Weber. It's a very long unit, and the speed will be omega radian per second. K will be a constant. So how it look like. And then we're also looking into the torque. The torque would happen to be proportional to a constant KT, and also be highly related to the magnetic flux. And then also related to the current pass through. Why is that? Because you can see that the current, this armature current, is the one pass through wire. When this wire interact with the magnetic flux, it creates the Lorentz force. that means is our torque. So that's why logically you can see that the torque is related to the magnetic flux, phi, and also current. And then later on, we can prove to you KF and these two constant, or constant, and back EMF constant KT and KE are equal to each other. They're also equal in the SI unit anyway. So later on, we can prove that. So that's very simple, straightforward derivation. We can all do that yourself. So that is to say, if we want to control a motor, usually we try to control motor torque, because high force, we can drive the motor in faster speed, high speed, or higher force to move the different item. So in this case, the torque is actually controlled by the magnetic flux, or can control by the current. If you drive the motor at high current, then you got higher torque. So that's the way we do that. That is to say, if you want a high power motor, usually the copper wire will be thicker, right? Because you need more current. Of course, you can put more number of turns in order to create more better flux linkage. So there's many ways you can do the job. So basically, there's the two important parameters, the back EMF and also torque equation. Yes?
I was gonna ask, were the two constants just kind of like because the values were proportional to for EA it was magnetic flux per volt and speed, for the torque it would be flux and armature current.
In next few slides, we're going to show you why they're equal to each other. But at the moment, if you're just checking the SI unit, they're equal unit. Of course, at the moment it's still rigid. We have not proved that they're equal to each other, but we're going to do that. So yeah, it's quite interesting. These two constants are equal to each other, except we can equal.
It's just I had a question about like if this constant is like the same in every case scenario or
For same motor, these two should be equal.
okay.
Of course, they're only for some good motor, for some RC motor, that may not be the case.
I see.
And
So they're equal to each other and they change based on the conditions such as like what motor we use.
that's right, different motor, they have different constants.
Okay.
Yeah, that is not a universal constant, that is constant for particular motor.
And is this same in ideal stance or is it just same in general?
It's same in ideal condition.
Okay.
But however, having said that, they are not that much different, only different by a few percent. So the most of the magnetic design or motor design is assume them to be equal to each other. It's good enough. You are good enough to assume them equal. Especially for undergraduate, we use assume them to be equal. But for postgraduate, then we know that they different by maybe up to 5%. So here will be a number of equations you need to understand all of that. Remember that. 100% remember that. Next equation. Anyway, so the first equation one, which is the first equation we learned just now, really important. And then since you got the voltage equation, next thing to examine the power. So voltage times the current, input current is power. Because the input current same as the armature current. So putting I here become this term, right? And then, so that means the EA back EMF is this one. So we can also put into this equation, become this equation now. So that's the input power. So you can see that input power have a portion go to this back EMF portion. Another portion will go to the winding. So that means this I square R is the winding losses, the copper losses. This winding go to the something else. So this something else must be related to the mechanical power output. Because for input power, we go to a motor, either become power losses or become mechanical output. So obviously, by observation in this equation, we know that this must be the electrical resistive power losses due to the resistor. This must be something related to output. We're going to go deeply later on. For the torque equation, that's mechanical torque we give you just now. And the torque multiplied by the speed will give you the power, output power, right? Then that's why we have this equation. So now then you see that this output power, the input power. So this equation, we see that this obviously the resistive loss due to the copper. you can see that if the copper is perfect conductor, there won't be any conductive loss. So everything will go to output. So now then, these two should be equal to each other under ideal condition, no restrictive loss. So if you equate these two, what can you observe? The two K constants are equal to each other. So that is the derivation I just guarantee to you. These two are equal to each other under a good motor. Yeah. So that's how we come up. These two are equal. So that's why I come up KTO equal to KE. So that means the motor torque constant are equal to the motor back EMF constant. Yeah, that's it. If you double check with any lecture notes, textbook or internet, they will say the same. So that's a really basic concept for all the DC motor. You all need to memorize. Not that many equations, only a few equations. Key equation in here, you can see that we remember the basic voltage equation for the DC motor. You also need to understand the back EMF equation, the torque equation. Only these three equations. That's it. That will be everything you need to know. The other equation, they are just follow from each other. Okay. You get that? So basic voltage equation, back EMF equation, torque equation. These three equations you need to memorize. Okay? From today, yeah. So next, we want to tell you some other thing about the efficiency. Anything related to efficiency is something we like to design. When you design a motor, of course, you need to think about how good the efficiency is. How do we control the efficiency? Yeah, as I mentioned to you many times, I like to design motor will be 90-something% efficiency, not 80, not 90, 90-something will be more reasonable. Then we can see how we can be able to do that. What is the control parameter? So obviously, efficiency output divided by input, then of course will be output divided by the summation of the losses plus the output power. Then for the output, look at that is the mechanical output power, the real mechanical power, and then plus the losses component, right? Or you can look into here, from here, that is the EA times IA is the one go to the winding. It's also your output power. Divided input power is this equation we saw just now, yeah? Input power equation. So that's why you can see that this equal to EA over EA plus IARA. So that's the two format of the efficiency. Both of them should be okay. Able to get the performance of the motor. Of course, there's many other formats. For the efficiency, you may devise your own format, but there's one of simple format you're able to observe how the performance of motor is. So you can see that all the parameters here are basically the physical parameter except the RA. The RA, you can able to control this and therefore improve the efficiency of motor because it's only the single loss component for the DC motor. So if you want to design a good motor, you need to think about, can I decrease the RA? If you want to decrease the RA, then you may need to use thicker copper. That would be another disaster because you increase the inertia and the weight of the motor. The copper wire actually will be located in the rotor. If the rotor is really heavy, of course, the dynamic performance of the motor is not that good. You need more force to start the motor, to speed up the motor, to control the motor. If you want to change the speed instantly, I want to have really light motor. Yes? So, for instance, if you want to move this tape, you want this tape to be really light so that you can do it rapidly. Same as in any motor. If you want to control motor really quickly, changing the torque, then of course you like to keep the motor have a really low, small size of the motor, lightweight for the motor. So that is to say, how can you control the copper? That's it, something contradiction. So that's how we're going to design good motor consideration. So give an example first so that you can briefly understand how we use all these equations. This equation is not complicated, very straightforward. So let's go for a quick example so that you all know what it is. Firstly, you got DC motor connect with 12 volt DC. And the armature resistance 5 ohm, you can measure it by using multimeter. So the armature resistance, we don't need any special instrument because they're all DC. So we're just using a multimeter to measure the resistance. So it's 5 ohm. The compounded constant, the K plus the phi is 0.1. So we're asked to calculate the armature current B to motor torque at 1000 RPM, output power D will be the efficiency. So that's a typical question we ask in the exam or in the tutorial. So that means here, we firstly change everything into SI unit. So 1000 RPM change in the radian per second first. So obviously you can know that it multiply 2 pi divided by 60 become 1004 radian per second. And then the back EMF EA is equal to the motor constant multiplied by the speed, that means 0.1 here, and then multiply 104 become this voltage. So back EMF 0 is offered 10.5 volt. So now then, you know, the input voltage is 12 volt. The volt drop on the back EMF is roughly 10.5. The remaining voltage must be voltage drop in the copper resistance. So that means here, you have 12 volt here, you got 10.47 here, then you can therefore get this portion, right? That means now then, IA times factor, RA is 5, so we can then calculate armature current, a simple substitution, then you can get current 0.3 amp of current. So this part A directly to use the basic voltage equation. Yes?
Is the armature current actually like the actual current, or is it just a idealized version of what current, how much current is doing?
It's actual current. You see the circuit is quite simple. We don't have any light transformer. We can refer the primary side, secondary side, they're complicated. So you can see that that's a really good question. The circuit is just that. This armature current is the one we calculate just now. It's not a transformer, so that's why this current is the real current. You can just use a meter to measure the current. The real current. Yeah.
So then at maximum or at equilibrium speed for the motor, there would be zero current at all.
No. The torque is proportional to the current. Even though in the equilibrium, when the motor running for a long time, what kind of torque is required? You don't need any acceleration, right? When your motor go to the final speed, what is the force related? We still need some force to maintain this basic movement, like all the frictional torque. Any motor, there must be about.
But like, if we're talking about like an ideal motor that has like, let's say no frictional losses, then it would just no current.
In theory, if you say the perfect motor, perfect physical condition without any friction, right? Then in this case, we don't need any IA to drive motor in the final state. That's the theory, but there's no such thing. Yeah. So now then we can get the current IA equal to this. Once we get the current, we can carry the torque. So this torque constant 0.1 multiplied by current, the torque is 0.03, right? So it's not very large value. It's very small Newton meter. So the torque unit equal to Newton meter, right? So next, we calculate the output power. Output obviously will be torque multiplied by the speed, will be 0.03 multiplied by the speed, then we can 3.2 watt of power. So the efficiency can get many equations to calculate. One equation EA over EA plus IRA, that means is here 10.47 from the EA, which we get from here, divided by the input voltage 1287. Of course, we can get it from mechanical power, output power. Input power always is the electrical. Input voltage 12 volt multiplied input current, same as armature current. Yeah, you can see in this diagram. Yeah. Input current from the input here, same as the armature current. So that means if you want to calculate input power, V in multiplied by IA will be the input power anyway. So that means go back to this equation. Then that is the input power. Here, output power is the mechanical output power, which is this one. So and then they also use 87.25. So other method will do. I just show you different method. One using electrical, one using mechanical to do that. So that is how we understand to use the DC motor. Very simple, straightforward, very simple equation, but you do need to manipulate a few voltage equation, torque equation, and also back EMF. So my comment to this question is, every tutorial question, not only calculation, I like to observe the phenomenon of the question. Like here, the efficiency is related to the winding resistance. Whenever you put copper, then you have winding resistance. So the thicker the winding, of course, better the efficiency. However, thicker winding, you increase the weight and the inertia and the cost. So that nothing can be perfect. So that will be pros and cons. So that is how we optimize the performance. We could compromise these two factors in order to prepare a good motor. One thing observe that the motor here is 87% efficiency. What do you think? Is 80% a good efficiency for motor? I would think more than 95. But why this motor is so poor efficiency? The parameter here is quite sensitive. It's not big up, it's a real parameter. The key problem here is the motor size is very small, 3.2 watt, small, tiny motor. 3.2 watt motor, really, really small, right? For such small motor, then there's a lot of the expenses in here, including the winding. So that means for huge motor, like electric vehicle motor, 100 kilowatt, usually really high. For those small motor, 3.7 watt, more like toy motor, simple motor, the efficiency usually is not very good. So 87% is sensible. So all the data here, so we always ask you a lot of question in the tutorial. Just like a simple tutorial, there's a lot of the implication. Firstly, you understand how to design motor. The thickness for the copper are related to efficiency. Another thing will be you need to ask yourself why the efficiency is not very good, mainly because of power rating. When you go for really high power rating, the efficiency usually will be much better. And then let's look at the torque and speed characteristic. So the motor basically we are driving the mechanical load, right? All the mechanical load sometimes we do prefer have constant torque to control them. Why is that? Because if you want to start a motor from standstill, we want to have a very high torque to drive the motor instead standstill. While we accelerate the motor, we like to have more constant acceleration. Constant torque means constant acceleration. If the acceleration is not constant, for instance, our vehicle is sitting there, if it is in non-linear acceleration, you will feel not quite easy. You have discomfort. So everything will be more linear acceleration, linear speed, you will feel much better. Good for human and good for the machine and good for mechanical system. In many cases, we like to have a controllable torque. So that means torque control will be important. Many cases, we also prefer have constant torque control. We can make sure that the torque will be linear controllable by the current. But if you compare them into gasoline engine, then they are not constant. So the curve for the gasoline engine, the torque is quite nonlinear, especially you cannot control the torque really well near the standstill. Gasoline engine at the 0 speed is really poor torque. So that means we cannot speed up the vehicle, gasoline car, rapidly from standstill. But for electric vehicle, we are able to do that. So again, in here, DC motor is proportional arbitrary current. So that is to say, if you want to control DC motor, we like to control the torque. Control the torque, we have to control the current. So current mode control is quite simple in electrical circuitry. Many ways you can control the current. Now you can control input voltage, you can control the current. So that's a really simple way to control DC motor. So all the motor in the market, those things are talked about before, like in this motor, the brushless DC motor, and also SR motor, synchronous motor, they all have a problem in the control. But this motor, very simple, very easy to control the torque, very simple to control the rotational speed. So that's why this motor still have very high market share. So next, we like to understand more about the torque equation, how the torque look like. So like in here, the back EMF are equal to this equation, right? Of course, equal to input minus the resistance here. So we can reconfigure that into this format. So that means the omega equal to this one divided by the torque constant. That's another format in here. Because we want to find how the speed relate to other parameters. So now then the torque equation is equal to this one. We just give to you. So I want to eliminate the armature current from this equation so that we can able to put these two equations together. So now then in here, IA here, I can replace the IA by the torque here. So now the equation becomes this format. So in this equation, the motor speed relate to this parameter. So this relate to the motor constant, usually a fixed parameter for given motor. Voltage can be constant or depend on how much voltage you input. And motor resistance, RA, for given motor is fixed. And then that means so we can now have a relationship between the speed and the torque, which is this equation 11. So this so-called the speed and torque equation, that's the equation we use it to control motor, to study the motor. So it's more interesting, we can see how the equation look like, how the motor behavior look like. So for all the motor study, we usually the first thing we like to do will be look into the torque characteristic, the torque equation, how the torque are related to the motor speed. Because this is the basic criteria, we understand all the motion control. So that's to say, when we want to have how we control the motor torque, how we can control by input. We cannot control by the resistance because it's fixed. So when the motor given, the resistance is fixed. The motor parameter here, K constant, also fixed. First, you design motor, the K constant will be fixed. The flux here, you may able to regulate, but however, if you use permanent magnet, you can't change the magnetic flux because PM is fixed, permanent magnet fixed. But however, if you use additional coil to generate the magnetic flux, you may able to regulate the flux. And then that's why you can see that correlation between this and that are mostly for different motor will be controlled by the input voltage. You can't control by some other function, you may control on this, depend on which type of motor. So input voltage, the key parameter you can control the DC motor. So that to say from this equation, what you can see will be if you're given with a motor, then you can really easily to control the input voltage. And then you can therefore control the relationship between torque and the speed. And then if you want to have further control, you need to adjust the magnetic flux. So probably in this case, you're not going to use permanent magnet. You have to use some other method to generate the magnetic flux. For simple motor, like many pulse motor or many home appliance, because they want to make the circuit control simple, they only use one phase to control it. And then if you want a high performance, like electric vehicle, then you have to also control the magnetic flux. So that's the basic control concept. So you can see that our original equation, the voltage equation, torque equation, and back EMF equation, these are three basic equations. This is the one you need to memorize, and then you convert into this torque and speed equation. From here, you also observe how you're going to control or operate on a DC motor. Okay. So next to do will be try to look into the characteristic. So from that equation, we can therefore convert them into linear equation.
which like y equal to mx plus c, right? So C1 is this constant related to input voltage. M is the slope here related to this one. So you can plot the graph become such a way, right? Linear graph. So all the control system, we like the performance will be linear. Linear control is much better for us to control everything. If non-linear control will be more complicated. We don't know how to control that. So all the people like the DC motor because it's linear control. For instance, in here, you can see that we have a motor here, back EMF motor resistance, the current here. So we can able to use input voltage to control them. And then the flux here, they're either using PM to provide the magnetic flux for the motor, or we can use a coil to produce the magnetic flux. The coil will be quite simple with a magnetic coil here, and adjust the input voltage or adjust this resistance, variable resistance. You can therefore control the magnetic flux. That's why you can also control the slope here. So either way we can do. So you can see that for both methods, that is a very straightforward, simple way to control a DC motor. Up to this point, any question? We plot the graph, we can see that when the torque equal to 0, like here, that the intercept, y-intercept is equal to this one, mainly controlled by the voltage, right? And also by the magnetic flux. Then you can see that when the torque get higher and higher, then we can see that the speed will become lower. So the manual control method, we can plot all the graph like this. So you can see that when we increase the input voltage, the curve of the graph will moving upward in such a way. So you can see that the slope here, the gradient here, M1 is unchanged because mainly controlled by the winding resistance and the magnetic flux. But however, when we increase the voltage, we therefore also control the motor speed. For instance, if you have a constant torque condition, if your mechanical load is constant torque, so that means say, so that means all the way will be this curve you are operating. So when you want to control, increase the motor speed, so you do at this voltage, to get this motor speed, if you want to increase the motor to next level of speed, you just increase the voltage here. And you increase further, you got negative speed. Increase further, you got negative speed. So basically, you can see this curve here, just to give you a concept. We can able to control motor under the constant output torque condition, but we just using the input voltage to regulate the motor speed. Simple and straightforward. And then of course, when the motor torque varies to other parameters, with high torque, then you can see the voltage also be very in such a way. So that curve is simple, straightforward. Basically, just come out from our linear equation. Then you can then understand how we control the motor. All right. Yes. That's a note of the operation, manipulation of the characteristic. So we can redo the characteristic by using this format, like the speed against the voltage. Because we know that we're going to use the voltage control then anyway. So for different value of the torque, the output condition, the torque condition, we can redo the characteristic become like this. Then the slope again, we just use 1 over K5. So that's to say, when the input voltage equal to 0 here, then the 0 speed in the torque will equal to 0. So when you increase the voltage, then you can see that when the torque will start to increase, and then the speed will also go in such a way. And from the equation, we also know that the y-intercept will be equal to this parameter. It's because in here we use the voltage to control the motor speed. So this field curve is just give you different parameter with how we control the DC motor. But anyway, you can see that mainly the control parameter will be the torque and also the motor voltage. For instance, in here, you can see that when you have a constant torque environment, then if you want to control motor speed, you can just change the input voltage, like in this curve. Or in other condition, previous condition, then you can also plot out the motor speeds against the motor torque. So two equations is the same, it's just different independent parameters to do that. So let's go for another example. Let's see how we make use of the torque constant. So this example, you say now you have DC motor and controlled by a variable DC power supply. The armature resistance is 1.5 ohm, and the combined torque constant K5 equals 0.1. The armature current is proportional, is controlled at 2M. So we have output controller control 2M. So now the motor speed and calculate the motor speed and the motor torque at 15 volt input voltage. And then the torque and speed, the torque and speed at input voltage equal to 20. So that's two cases. If you calculate the torque and speed at 15 volt, next, if you want to control them to 20 volt, what will be their parameter? So in either case, how do you comment about the efficiency and explain your observation? So that's how we can see here. So the back EMF equation, E equal to K omega again. So that's really basic equation. Then the voltage equation also equal to this. So input 15 volt, the motor constant is 0.1 here, and multiplied by the speed, which is the one we're going to calculate. The current is 2M, so 2M multiplied by the motor resistance 1.5 will give you 120 radian per second. So that means at the voltage control, 15 volt, you can able to obtain 120 radian per second the speed. The people, they may not understand radian per second. We convert them into RMS, rotation per minute, right? You know RPM. So that would be 1145 RPM. So basically, we just need to multiply by 60 divided by 2 pi. And the motor torque against motor constant, multiply the current, equals 0.1 times 2 to 0.2 Newton meter. So efficiency, you can use this equation, so which is EA voltage, back EMF voltage, which is 15, minus the resistive drop, is this one, and over 15. So that would 80%. So that means in this condition, part A, when the input voltage 15 volt, then efficiency is only 80%. The motor speed is 1145 RPM. So more interestingly will be if we use voltage control to increase the motor voltage to 20, what happened to the motor? That's something we like to observe. So the concept for this tutorial to tell you what is the performance of motor when we vary the voltage. The voltage control vary the voltage. So like part A, 15 volt, part 2 with 20 volt of voltage. So part B, let's redo everything again to see how the performance look like. So now we increase to 20. So 20 volt equal to, again, 0.1, torque constant, multiply the speed, plus the volt drop here. We control the current at 2M, so 1.5 resistance, now the speed equal to 170, and then change them into RPM, then we have 1623 RPM. The motor torque is now also use 0.1 motor constant, multiply the current 2M, then it becomes 0.2 Newton meter. The efficiency again, we have 20 volt here, minus the volt drop on the RA. A higher current got high volt drop divided by 20. So now we got 85. So you see that even though we got high volt drop, because input voltage is higher, so the contribution from the RA will become less. So that's why the efficiency is now become 85 compared to previously 80. So in here, the quick first observation you can get here will be when we have high voltage, we got higher efficiency. That's quite common because I always tell you for many motor design, we can be high voltage. Like in the electric vehicle, Before we only use 50 volt, 100 volt, Tesla using 450 volt, but the latest design using 800 volt because they want higher performance, higher efficiency. So this simple example to show you, when we increase the voltage from 15 to 20, the efficiency already increased from 80 to 85. And the speed, you can see the speed from 120 radian per second now increased to 170. So that means we can use simple voltage to control the motor speed. And then you can also observe that the efficiency can also be increased in such a way. So you can see that efficiency of 20 is much higher. So you can see that we control the current, armature current, so the armature will be unchanged. Yeah. The torque is unchanged in two cases because we're using current mode control. The torque is proportional to the current. So under the torque is controlled, but the voltage applied across RA remain unchanged. But because the voltage drop in the RA as related input voltage will be much smaller. So actually you can see that the proportional power loss compared to the input will be much less. We therefore have higher performance in the efficiency. But of course, the input voltage also relate to the back EMF here. Because whenever you have higher input voltage, then you can able to control the speed to be higher. Once the speed become higher from 120, increase to 170, then both item will be changed for the motor. When the motor speed increase, in the motor equation, which parameter will also increase. So here we say torque is the same because torque proportional curve, right? Back EMF. Back EMF. The back EMF proportional motor speed. So now the back EMF also increase. So that the reading will increase output power. So you see output power for high performance, we like the motor have a high output. Yeah. So for same condition, if you're able to increase the output power for the motor, that's how we improve the performance. So under the constant current, we know the torque is unchanged. But however, if here we are able to increase motor speed to high up, so that means the output power can increase. The output power related to the torque multiplied by speed. Now we increase the input voltage, we therefore increase the output power because the back EMF already increased. So the speed already increased. So that's how the phenomenon we observe from this simple tutorial how we're able to control motor efficiency. So that is to say how to control the motor efficiency. Firstly, you can see that increase the input voltage, right? We can usually increase the motor efficiency. Secondly, once you increase the input voltage, you can definitely increase the motor speed. Increase motor speed will also increase the motor efficiency. But from the previous tutorial, we found that we want to decrease the voltage drop on the resistance, armature resistance. So that means if you want to design, you're able to reduce the RA, you can also improve the motor efficiency. So mainly about this field parameter, that is to think about in the future when you design a motor, how you improve overall performance. Then high voltage motor, right? Of course, high voltage motor will be something we need to do. Let me write down the key. So efficiency are related to higher voltage, right? Or lower RA, or also higher speed. So the tutorial is really simple. It's a very basic voltage equation motor. You have three basic equations. Do you remember that?
input voltage equal back EMF plus IRA, right? And the back EMF equal to the torque constant multiplied by the speed, right? And the torque equation equal to the motor torque constant multiplied by current IA. Only three basic equations. And from three basic equations, we can therefore derive a lot of the theory here. The theory including how to control motor, how to improve the efficiency, how to look into the efficiency of the equation, how to understand torque and speed characteristics, how we control the motor by using the voltage control and the magnetic flux control. Right? So three simple, really simple equation, we can able to get a lot of the research topic from there. So even the DC motor, so many work will be done. So marvelous, right? Oh, the first equation always Ohm's law, simple Ohm's law, right? Everybody knows. But there are so many things come out from this simple DC motor. Interesting? Any question? Anything you would like to discuss further for the DC motor? Good. Yeah.
I got a question.
Yeah, please.
You know, like a regular DC motor and a brushless motor, what's the difference between it?
Yeah. We're going to teach you the brushless motor in this few moments. But basically you can see that we are using this motor, we can see the commutator in that brush there, which help you to control the direction of current. You need to control the current so that after 180 degrees, then you can reverse the force direction. Right? So that's the basic thing, basic item, how we use the commutator brush to do that. The commutator brush is a really basic design for this motor. Before we develop power electronic control motor current, then we only use this method to control the motor rotation. So this motor has been there for 20 years. But we still are using. But however, once we develop the brushless motor, then we found that we can actually not use mechanical commutator, but we can use electronic commutator, which is power electronic switching to perform the changing current direction, which you can learn it after a few weeks. In the after the midterm, you're going to learn it. So the two major difference will be if you don't have any carbon brush and commutator, you use that component. This component needs to be maintained with after everyone to figure you think at home. When you have a washer, maybe powder, sometimes you find it not working really well because no power. You need to change the carbon brush. Yeah, I think you sometimes you need that. So that's key thing we don't know that. And also when you go through the tilting current, there will be some active cause fire burning for the carbon brush. And also the dynamic response is not very good because you change the current mechanically. So you don't have active method to change the current instantly. And that's why when you come with the power electronic control the motor current, that's much higher performance. You can see this motor, once you use carbon brush, you can't have even high-speed motor. This kind of motor are 300 RPM, 3000 RPM, quite a maximum. This is carbon brush. But as I mentioned, if I want a high performance motor, that means high speed, not 3000 RPM, 30,000 RPM, then carbon brush no way, impossible. It's mechanical contact.
Yeah,
How to say that? So we have two electronic contact that is consistent.
It's like two of the like a pin that's like connected, not connected, but it's like brushed onto the that's spinning.
We use purely just want to say to recreate all the situation. So we're going to learn this really soon. We're going to show you brushless this motor. So of course, because of this commutator brush, then people develop the induction motor. AC induction motor, you don't need to use any carbon brush. So that's the one alternative. But of course, AC motor do have other hurdle and issue. So that's why we eventually develop the brushless DC motor, which is even better. So that's history of the development. And let's go to next stage.
So now then we can look into the fuse circuitry. And for Let me erase this first. So there's a number of ways you can therefore control the magnetic flux for the motor. So one thing you can observe that before we always talk about permanent magnet, we are using permanent to provide you magnetic flux. So that will come up initially. Just now when you look into the torque equation. So when the torque is constant, you only can control the motor using voltage. You own a single parameter. That is not that flexible because the voltage can be a DC source. Then you want to adjust the DC voltage. It's not that easy to adjust the DC voltage without power electronics. You may use a resistor, potential divider is not really convenient. And then sometimes prefer to use the magnetic flux control because magnetic flux is also one of the control parameters. But using GM, you don't have that flexibility. So that's why many motors actually they're using a separate excited or another coil to control the magnetic flux. So like what we mentioned here. So basically you can see there's many different types of motor, including firstly the separate excited DC motor. We have separate winding to generate magnetic flux. Or of course the PM motor also a part of the separate excited DC motor. And then because we had additional coil, we also armature coil really inconvenient, have two electrical circuitry. So people try to make it simple. They will connect the field winding, the magnetic flux winding, in series with the armature winding. So we only have one power source connect to both. That makes things easy and simple. So that is called series motor. Series motor means connect the field circuit and armature circuit together in series mode. Very simple. And then if you got series of coil, you have parallel connection, the shunt. Shunt will putting the field circuit and armature circuit in parallel, in shunt. So we call it shunt DC motor. And then these two do have some pros and cons. So with another guy will try to put them all together, series and parallel. So become a combined motor, it's called a hybrid version. So let's look at each of the case. So all four of them are very popular. A lot of people to use different configuration because they want to make the circuit simple. In this case, they don't need to use two DC sources to excite the motor. PM is okay. PM, as I mentioned before, we have less control capability because flux is constant. And PM is really expensive. Especially, you know that PM, we are using rare earth material. Sometimes rare earth material is really expensive, really controlled by many countries. So that's why we tend not to use that many PM. PM is easy, simple. So here will be a configuration for separate excited DC motor. So basically you got the armature here, then you will have a field winding. The field winding provide magnetic flux to the motor. And this field winding just like magnetic coil. And then we have input voltage for the field voltage, and then we can just using resistor. You can either change the voltage here or change the resistance here. The field current usually have much less than armature current, usually in design. So that means for this circuitry, you don't need to use huge current to control them, only really small current. And that's why the RF, the resistance for the field circuit is also low power resistance, low power circuitry. Usually only half, only maybe 10%, 20%, that should be good enough for this kind of development. Then you may say, why we can able to develop such high magnetic fields? Because we use many number of turns. If you increase number of turns, then of course we generate a higher magnetic flux. We don't need to have high current. So that's one of typical circuitry. So obviously you can see that instead use same PM, we can using two independent DC source to provide one here and one here. So the power level for these two are different because they control different circuitry. The good thing is here, we can separate independent control of armature current. Because armature current, we can able to control the motor torque. And field here, we can also control motor torque and also the back EMF separately. So that is to say we are able to control the field, we control armature current independently. So the field here can be really simply adjusted by the simple field circuitry like in here. The field voltage divided by the field resistance. Because you're talking about here is DC, so that means this equation is also DC equation. So voltage divided by current, because the pure inductor, you don't consider this internal resistance. The internal resistance all at here. So we can just find using this method to control or calculate the field current. This field current is related to the metal flux. So metal flux and the field are proportional to each other. We got another concept, but it not appear in here. So that's how we're able to use separate method to control the motor. And series motor will be like that. You can see that we have the field coil here connect in series. So obviously you can see that the current of IA, armature current, will now become equal to IF. So that means you have less control capability. You can't independently control IA and IF. You need to put them together. Key reason you do that because we want to reduce the cost. Because if two separate circuitry could be really expensive. But if you put them together, then we can save one input source. But we need to find a way how to compromise between IA and IF. So you can see that the voltage equation, input voltage, will therefore equal to field voltage here, plus the back EMF, plus the work job in the armature resistance. The advantage you can see that here, the starting torque can be quite high. Any people can tell me why the starting torque can be quite high? Because we see the torque are also proportional to the flux. So during the starting, the water here will be, when the starting, the speed here will be 0. The back EMF here will be pretty small. So we got huge current will pass through the whole circuit. Large current, that means when we start motor, the starting resistance will be much higher than the steady state external resistance. So that means when the starting current here is now, we've got large IA here, large field here, large field, we've got large metal flux. So that's why we're able to create a high starting output of the motor system. Some motor may not be able to provide you with a high starting torque, but this series motor are able to do that. So that's why in the comment here, the torque is proportional fast, but they're able to create a high current in the motor starting. So, and this circuitry, firstly, we use a single circuit to make up the two portions of the motor design. So, and this motor, instead of the two separate circuitry, when we have more circuitry, then control, electronic, everything will become more complicated. So, single circuitry will be much preferable to make it something simple. So, this motor can be able to create us with the speed control quite well and also high torque. But the motor speed regulation obviously will be lower poor because we are mixing field current IF and also armature current. So originally we're able to control the speed by input voltage. And then we're able to control the torque by the current. But now the current being used by both the metal flux. So if you want to increase the torque, you want to increase the current. But once you increase the current, then the flux will increase, then the torque will also be increased. So that is something not coordinated well. So this motor is simple and has been used in the market for a long time, but however, may not be too applicable by all the applications. But which application we still think will be more advantage? We mentioned about starting point. So the motor becomes stable. Then this frame member becomes much larger. Then the field current or the IV current become much lower. Because when the motor going in a steady state, we don't need that much torque. The torque don't need to do any acceleration. So high starting torque mainly to accelerate the motor from standstill to the final speed. So for this application, what type of motor would that be for which application? So what is application for this motor? For this kind of firstly,
Sheet.
Huh?
Smaller sheet things that probably.
you did think about those applications for high starting torque. Which one will be for really high starting torque? Mainly for small machine torque, you don't care too much about it, right? That will be for traction or train, electric train. For train, you see there are so many coaches that are so long, with the highest the torque, the starting is huge, much higher than any machine. So that means when the train starts with zero, the inertia, everything is so heavy, you really produce current to operate it. But when the train goes to the final speed, the friction, any friction, you don't need much torque. So that's why the IA and RF can be good. Yes?
For electric trains, are they mostly like DC like this, or are
Oh,
they mostly like
yeah.
DC?
And for train, we do have DC motor, we do have AC motor, both of them coexist. I think not very half and half. But we do have a lot of DC motors. Why is that? When DC motor is more conventional motor have been there in the market. So that means for many of the older generation, first, then they tend to use the DC motor. So you can see that many trains, they are using DC voltage, 750 volt. So that's also quite common. So, but later, then once we develop industrial motor, AC motor, many people switch to this kind of industrial motor. But industrial motor are also quite considered for the control. So later on, when we go for this industrial motor design, then the thing about it's really difficult because we don't have punch curve, we don't have any field curve, so we cannot control the speed and the torque level for industrial motor. So the control is very complicated. But however, in digital development, we do develop the industrial motor control method called the vector control. It's a wonderful control method. We're able to make the control of this industrial motor really simple. So that's my one thing. That technology we start to use industrial motor for all the train and also electric vehicle application. So now they both of them will coexist. I think when they get in the later stage, I think we will have more AC motor in the train and electric vehicle domain. But anyway, this series motor still very popular, low cost, because you can see the configuration, you don't need that many parcels, only one parcel. So and then we also have the shunt DC motor. But before we go, we only 5 minutes. I want to switch to the lab tomorrow. If anybody like to go for the lab tomorrow. So let's stop it here. Then we continue this lecture. But before we go away, then let's look into that labs thing.